Today we take a deeper dive into digital logic with a new kind of logic, sequential logic. The logic we've seen before we referred to as combinational logic, which means that whatever input we gave it completely determined the output that came out of the circuit. In sequential logic, however, the same input can yield very different outputs depending on the current state of the circuit. For example, let's take a look at this input and the current state of Dad. Chances are, with Dad in that kind of a state, we will get the keys to the car. But what if Dad were in a different state? No keys tonight. The same input, but the output depends on the initial state. Now, there are other ways that we can actually change the state of Dad. Say, with this kind of input. Dad's state changes. We could probably change the state back, too. Yep, same old Dad. Out of the family life, back into digital electronics, let's take a look at this circuit. Notice the real interesting wiring going on here. The output of the OR gate is turned back on itself and becomes an input to the AND gate, and the output of the AND gate becomes an input to the OR gate. It's a loop. Let's fire up the circuit with zeros on the inputs. You'll see that every part of the circuit is a zero except for that little wire between the NOT gate and the AND gate, which has currently got a 1 on it. Let's change R to a 1. Well, that wire changed, but that's it. Nothing else changed in the circuit. We change it back. Again, nothing happens. So if the output is already 0, doesn't look like R does anything at all. It can go from 1 to 0 to 0 to 1 as many times as we want, and nothing else changes in the circuit. Let's try S. If we change S to a 1, the OR gate is going to go. That's going to change that feedback wire to the... And now the AND gate. So not only did it change the output, it also changed the internal state. Those crossed wires have changed as well. Let's see what the result of that is. If I change S back to a 0, the 1 stays in the output. Change S back to a 1, still a 1. Back to a 0, stays a 1. So it looks like what happened here is that when I set S to a 1, it changed the state of the circuit to a 1, and now I can't change it back just by changing S to a 0. But what if I changed R to a 1? That one goes to 0. That turns off the AND gate. That, in turn, turns off. And the state 0 is now locked into the circuit. Again, changing R to a 0 doesn't do anything else. So R, set to 1, seems to force the circuit into a state of 0. S forces it to the state of 1. We call this simple circuit a set-reset, or SR, flip-flop. If I want to flip it to a 1, I just poke it with a 1 on the S. If I want to flop it back to a 0, I poke it with a 1 on the R, or the reset. Now we're going to take a look at this circuit in a truth table, and you may want to actually build it in Logisim and follow along as we're building the truth table that goes with it. If you do want to do that, pause here, build this little circuit, and then resume the podcast. Okay, note that on my truth table, I have not just the inputs S and R, but also the state, the initial state. And there are 8 possibilities now, considering that I have those 3 different things that can vary. We'll fill them up in counting order like we always do. When we first built the circuit, it was in state 0, S and R were also 0, and the state remained 0. Nothing happened. Recall that when we set R to a 1, or reset the circuit, nothing happened. The state stayed a 0. And so we could go back and forth between these 2 rows of our truth table just by toggling R back and forth. When we toggled S to a 1, however, we transitioned to that new state. Everything turned to a 1 inside the circuit, and we got a 1 coming out of it. Notice what that means. We are actually moving from one row of our state table to another because our state has changed. S and R have not changed, and it's a good thing, too. If they changed at the same time, maybe to set it back to a state of 0, we could flip back immediately to the other state, and we'd be lost back and forth, toggling between states in what's known as oscillation. Be careful with Logisim on the lab, because you might get caught in oscillation as well. Now, when we set S back to a 0, we saw that we were still locked into that state 1. And the only way for us to get back to state 0 was to set R to a 1. And sure enough, that takes us to state 0. And you can see that transitions us back up to a different row on the state table. Now, we didn't really talk about what happens when both S and R are set to 1, and that could obviously happen in either of the 2 states. If you built the circuit in Logisim, go test it out. See what happens under those 2 conditions. Pause the podcast and come back when you've got your answer. So, if you did that, you can see what happens in both cases is we end up in state 1. It transitions from state 0, and in state 1, it really does nothing. Truth tables can sometimes be a little tricky to follow for sequential logic. A state diagram is a different way of looking at it that sometimes makes it clear what's going on. Here we're going to translate our truth table into a state diagram. The state diagram starts by a large circle representing each state. This flip-flop only has 2 states, 0 and 1. And we're now going to step through the truth table looking at what happens in each state transition. Well, you can see that if we're in state 0, and we have inputs of either 0, 0 or 0, 1, we stay in state 0. And we represent that by the little arc shown labeled with the inputs. Now you can see if we get either a 1, 0 or a 1, 1, we transition to state 1. That takes care of all the possible things that can happen when we're in state 0. Now we're going to look at state 1. Well, 3 things there cause us to stay in the same state. 0, 0, 1, 0, and 1, 1. And only one combination of inputs, 0, 1, takes us from state 1 back to state 0. You can see that the state diagram that we're left with contains all of the information that was originally inside the truth table, but it's a little clearer about what's going on as we transition from state to state. In fact, we could simplify it further just to this, and we know that any transitions that are not shown, any inputs that are not shown, just represent staying in the same state that we're in. So there are really only 3 inputs that define what's going on. Now we look carefully at those first two inputs, and what distinguishes them is that S is equal to 1. That's the purpose of the set. As long as we have S equal to 1, it doesn't really matter what reset is. If we're in state 0, we're going to transition to state 1. In state 1, the only thing that causes a transition back to 0 is to have S equal to 0 and R equal to 1. And the state diagram is generally represented without the individual bit patterns, but only that analysis we just completed. So our set-reset flip-flop can be described in a very simple way. With S and R equal to 0, our state stays the same. If S is equal to 0 and R is equal to 1, we reset to 0, or force our state to 0. If S is equal to 1 and R is equal to 0, we force our state to 1. And officially, 1 and 1 is undefined, but as we saw, it always sets us to state 1 in this particular implementation. Now, using the power of abstraction, we can take that circuit that we've just created and call it a set-reset flip-flop, and then we don't need to worry about the details of its implementation anymore. This is exactly what you're going to be doing in the final lab of digital logic when you build a particular type of flip-flop and then use it to create a memory circuit. Now, we're going to start with a circuit like this. Very often what we want to do is we want to put some combinational logic on either side of it to get exactly the effect that. So here's some combinational logic that could cause particular inputs to happen, and I could also put combinational logic on the outputs to have something else happen. Notice there's no rule that I just have to pull one output from the state. I could pull both outputs of the state if that turns out to be useful in a particular circuit. This should set you up now for the final lab in this unit. Good luck.